All right. Let's write this as a theorem. Uh, any metric space xt has a unique completion up to isometry. Okay. And let me give the proof. So first we define. I'll just follow the setup I described above. First, consider the map J from uh, X to Bx, uh, defined as follows. So I will associate any element of the metric space to a function. So Jx will be just a function, and this function is a function on X. Defined as follows. Uh, okay, let me here first consider the map. Uh, let's say fix. Uh, okay, fix some point x0. Okay, x0. Then j of x, we will denote it like this, is a function from x to r defined by. So I have to tell you what is the value of f of x. F of x at any point y is just the following: distance from x to y minus the distance from y to x0. So what is this function? This function does the following. You give me a point. Okay, first we fix this x0. We will never change this. And then whenever you give me a point x, I consider this function f of x. This function will depend on x only, and it is defined as follows. Since this will be a function, it should take a real number value at all points of the metric space. So whenever I am given a point, I measure this distance, and I measure this distance, and I look at the difference. Okay, so this is a real number, and it is the value of fx, this function, at the point y. But here you see I claim that this fx is a bounded function. So first of all, I have to prove that, you know, why this is a bounded function, because my notation, right, tells me that fx is a bounded function, and it should be justified why this is bounded. The reason is the following. The distance between, so note that the absolute value of this real number, which is just the x, no, yx minus x0. What is this? Well, this is less than this real number, right? X 0. This is basically the triangle inequality, right? This is true for all y in x. Therefore, the values of this function are less than or equal to this number, a fixed number. Hence, fx is a bounded function. Function on x. If you don't see this, this is something really easy. Let me write it here. You see, dyx is less than dyx0 plus dxx0. And therefore, if I take this to the other side, we get dyx minus dyx0 is less than dxx0, right? Xx0. And then if you interchange x and x0, if you interchange x and x0, you get dyx0 minus dyx. And if you change x and x0, this doesn't change. So what you see is then this number, common number, is both greater than this number and it's negative, right? This is just minus 1 times this number. So this number is greater than this and it's negative. Therefore, this is larger than its absolute value. Okay, so that's the explanation. And this tells us that this is a bounded function. Hence, this j is really a function from x to bx. Okay, and then we claimed it. Claim j is an isometry. So if I have 2 points, then their images here are 2 points, and the distance between the 2 points of x is the same as the distance between the images of those 2 points in bx. So that's my claim, and this is as follows. This can be written, this can be done as follows. So okay, proof, take any points x and x prime. Okay, then what is this? Fx. Then for any y in x we have, so what is f sub x y minus f sub x prime y? Well, by definition, f sub x was what? F sub x is just dxy minus dxy0, that fixed point. Okay, so what is this then? This thing is just okay, dxy minus dy x0, and I subtract from this dx prime y minus d y x0. So these are the same, you see that, right? These are the same. So this is just dxy minus dx prime y. But you see, this is just the above term here with this we just saw, right? This is similar. This is the same thing basically. So this is less than distance between dx and x prime. Okay, so and this is true for any y in x. Therefore, uh, the this is less than for any y. The absolute value of this gadget will be less than this number, because if I replace again x and x prime, this will be multiplied with -1, but this won't change. Hence, indeed, or maybe hence, so this distance is less than dxy, dxx prime, for all y in x. Therefore, the supremum is less than this. Hence, thus, d sup of fx and fx prime, right? The supremum metric, which is just the supremum of uh, all these gadgets, this is less than dxx prime. Sorry. However, if I let, however, uh, this difference. So if I let, if we let y equals x prime, then we get what? No, maybe I should say x. Then we get what? This difference. So what is this? This was dxy minus dy x0. No, yeah, and then x prime y, right? But I let x equals y, so this is just 0. This is just 0 minus dx prime x. So this is just dx x prime. So what I see is then this supremum is less than this number. However, one of the real numbers in the set over which we take supremum contains this number, right? So this expression is equal to this if y is equal to x. So this set already includes this. Therefore, its supremum is not less than or equal to this, but actually it is equal to this. Hence, the supremum metric between f and x prime is really x and x prime. Okay? So this means what? In other words, the map J from x to bx, sending x to jx, which is f of x, is an isometry, because distance between 2 points is equal to the distance between the images of this point. So this is an uh, isometry. Okay. Now let x tilde to be just the closure of the image, okay, in bx d sub. this closure is a closed subset of bounded functions, and we know that the metric space of bounded functions with the supremum metric is a complete metric space. Therefore, x tilde is a complete metric space. Since Bx is complete and x tilde, it is the closure of something, is a closed subset, is a closed subset. X tilde with the supremum metric is a complete metric space. And moreover, the closure of this is equal to x tilde. So that it contains an isometric copy, I should say maybe, okay, an isometric copy Jx of x as a dense subset. So this is like real numbers, and Jx is the uh, set of rational numbers in real numbers. Okay, so this essentially proves half of the theorem. What was the theorem? Any metric space has a unique completion up to isometry. We proved that it has a completion. Uh, Next, we have to show that it is unique up to isometry. Okay, so I can construct a completion. You may construct a completion. Somebody else may construct another completion. But if these completions are totally different objects, then calling one of them the completion wouldn't make sense, right? We have to say that uh, if it is the completion, then so if you say that R is the completion of Q, uh, this suggests that actually it is the unique completion, right? Somebody else cannot construct a completion which is totally different than real numbers. Okay, real numbers is the completion of rational numbers. So we have to prove that. Have universal property. Completion of a metric space is unique. So this uh, completes the existence part of the proof. For the uniqueness, we will proceed as follows. I'll just start with two completions and then show that these two completions are the same up to isometry. In other words, I will find an isometry between them. Okay, so uh, let XD be a metric space. So I'll consider a different setup and assume that x tilde 1 d1 and x tilde 2 d2 are complete metric spaces, metric spaces, J1 from X to X1 tilde, J2 X to X2 tilde are isometries, 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 uh, so that the images of these isometries are dense. Okay, so I assume that kind of rational numbers has two completions. Okay, I constructed one completion, you constructed another completion, and I claim that they are actually the same completions. So what I will do now, uh, we must, evet, uh-huh. uh, yeah, we will consider isometric metric spaces as the same, okay? Because what is the difference between two isometric metric spaces? The elements have different names, but all the properties are the same, right? You just call that element something else. So the isometry should be considered as a what? As a dictionary, right? From one space to another space. But this, so this is a bijection. Every element in X has a corresponding element in the other metric space, and vice versa, and the distances are preserved. So we will consider this kind of metric spaces to be the same. Haklısın. Yani rasyonel sayıların aslında bir izometrik kopyasının completion'ını elde ediyorum. Ama izometrik kopya, hani metrik uzay anlamında bakarsan aynı görülebilir. Sadece isimleri farklı. Tamam mı? Peki. Ne yapacağım ben? Must construct theta 1 from x1 tilde to x2 tilde, theta 2 from x2 tilde to x1 tilde. Bunlar izometriler olacak. Isometries. Isometries. So that birbirlerinin tersi olacak. Yani theta 1 ile theta 2'yu kompoze edersem bu e, x2 tilde'nin identity function'ı. So this composition is the identity function of x2 tilde, and this is the identity function of x1 tilde. And finally, I have to have this. So all these constructions commute with this inclusion. So here I have, let's say, J1, J2. Here I have X2 tilde, X1 tilde, and here I have this gadget. So this is theta 1, theta 2, and this diagram commits. So if you follow arrows this way or this way, you will get the same number. In other words, J1, so if you go with J1 first and then theta 1, you get J2, or If you do it this way, you get J1. Okay, first with J2 and then theta 2, that is J1. So this means x1 and x2 are isometric, and the way they contain x is the same. Okay, uh, so they both contain x, but the way they contain x is even the same. Okay, so this is justified with this conditions. How can I construct theta 1 and theta 2? Well, we will do it this way. Uh, Remember, we spent a lot of time to prove the existence of a extension of a function, uniformly continuous function, right? To from a dense subset to the whole space. We will exactly use that gadget here. So uh, construction of theta 1, well, construction of theta 2 will be the same. So uh, J, so let's say A to be the subset of Jx in x1 tilde, right? Okay. We know that, uh, so its closure is just x1 tilde, so that A is a dense subset, and I have the following map, right? You see, uh, we have map from x to x1 j1 and x to j2. Now I'll do the following. So here I had x, and then here with j1 I go to a, and this is a subset of x1 tilde. But you see, I have a map from x into uh, x2 tilde, right? J2 and J1. So this is just okay. This is just J1 of x. J1 of x. Therefore, okay, let me write it this way. J2. So I have. Therefore, this map has an inverse because this is a one-to-one onto map. It is continuous. Its inverse continuous. So J1 inverse is a map from A to X. I have here J1 inverse. This J1 is inverse is not defined on X1 tilde. It is defined only on this subset. However, you see, if I combine this inverse with J2, then I obtain a map from A to X2 tilde. What is this map? This map is just J1 inverse. Okay. First, I go with J1 inverse and then with J2. Okay, so I go from A to X and X to X, X2. And I know what? J1 is an isometry. Well, its inverse will be an isometry, and J2 is an isometry. So both of them are isometries. Their composition will be also an isometry because each one preserves the distance between points, both J1 and its inverse and J2. Therefore, the composition will preserve the uh, distance. So since each Ji is an isometry, So is J2 J1 inverse. Well, now this map is an isometry. In particular, it is uniformly continuous, right? Isometry just preserves the distance. So if you choose your delta to be the epsilon in the definition of uniform continuity, you see that an isometry is uniformly continuous. So in particular, J2 composition J1 inverse is uniformly continuous. Now we have exact setup in the proposition or theorem we proved some time ago that I have a metric space I have a metric space, uh, a dense subset, and on that dense subset I have a uniformly continuous function into a complete metric space. Then that result told me that this function has a unique extension to its closure, which is x1 tilde. And if the map you started with is uniformly continuous, which is the case, then extension is uniformly continuous. Moreover, if it's an isometry, then the extension is an isometry. So uh, by by the extension result, we proved, we have proved earlier, there is a unique map theta 1 from where to where, x1 to x2, x1 tilde to x2 tilde, so that theta 1 at x is equal to j2 j1 inverse whenever x is in A, which is j1 x. So what we see is this. Now, uh, this map is defined on a subset of x1 tilde, but we have seen that there is a unique map theta 1 from x1 tilde to x2 tilde, and this map agrees with this j2 j1 inverse on the dense subset A. Okay, of course, the same construction goes the other way around. I can replace the roles of x1 and x2, and this time I'll get a theta 2, right? Similarly, we have, oh, okay, I know also this unique map. Moreover, is an isometry, since J2 J1 inverse is an isometry. Okay, that was a part of the proposition we proved. Okay, well, similarly, there is an isometry theta 2 from x into, no, theta 2 from x2 tilde to x1 tilde, so that x2 tilde is equal to, this time, j1 composition j2 inverse whenever x is in, well, not A, let's say B, which is j2 of x. Okay, j2 of x will be a subset of x2 tilde, of course. This is a subset of x2 tilde. This, same setup. Okay. Well, now I have x1 tilde here, x2 tilde here. I have this theta 1 map here, an isometry. Theta 2 is another isometry. And I have here x, and here we have j1, and here I have j2. Okay, right. And what we know is this. Uh, if I start with an x here, element here, so uh, if x is in x, then uh, if I go with first, let's say j1x and then theta 1, right? This is just j2x, and why is that? Because theta 1 is just you know uh, theta 1 is just j1 inverse j2. So if I put here uh, j1 of something, then I'll just get, they will cancel each other, I will just get j2, right? And this thing, so I should write it this way. This is j1x. Okay. Uh, am I done? Well, I am almost done. The only thing I need to prove that these are inverse of each other. Okay, theta 1 and theta 2 are inverses of each other. How can we prove this? So uh, we just, to finish the proof, we need to show that theta 1 and theta 2 are inverses of each other. But you see, uh, if x is in A, so if x is in A, uh, theta 1 is given like this. Okay. Then uh, then x is of course what? Maybe I should say it this way. If x is in x, then uh, theta 2 of theta 1 of j1 of x. So I start with an x here. I go here, and then I go with theta 1, and then go back with theta 2. But I know that on the elements of x, uh, you know, this is what? Theta 2. This is identity, right? Theta 1 is just, so this composition is just j2. This is just j2 of x, and this is just j1 of x. So that, so if I start with an x here, its image is here, j1x, and on J1x, this composition is identity. Hence, theta 2, theta 1 is identity on A, and similarly, theta 1, theta 2 is identity on B. But A is a dense subset of, so I have this theta 2 composition theta 1. This is a map from x1 tilde into x1 tilde, and this map is identity. This map is identity uh, on A. So this is equal to x for all x in A. Then we have what? So theta 2, theta 1 is an extension of identity function from uh, A to A. Okay, to x1 tilde, which is the closure of A. So, however, you know, on the other hand, identity function of x1 tilde is also an extension of identity on A to A, right? A is a subset of this space, and I have the identity function on A, and this function is an extension of that identity function. However, I have an obvious extension of the identity, which is identity of the x1 tilde. So I have two extensions of a function defined on a dense subset. But we know that on a dense subset, if you have a function and if you have extensions of these functions to the whole space, then they are the same, right? Extension of a function defined on a dense subset is unique. Therefore, that was the proposition we proved earlier than the one I used here. Uh, okay, what was? Let me try to find it. Okay, where was it? I think we passed it. Let me see. Okay, this proposition. A continuous function f from a metric space to another is determined by its values on a dense subset. Okay. Yeah, and then we had this one. So I am using the above result, actually, the simpler one. Sorry. Okay. So this function is the extension of the identity function. Identity function of x1 tilde is also an extension of this function. A is a dense subset of x1 tilde. Therefore, these two extensions must be the same. Hence, this extension must be identity of this. Similarly, the other composition, uh, theta 1, theta 2, theta 2 must be identity of x2 tilde. Okay, similar arguments. And this finishes the proof. Okay, so this will conclude this chapter. In the next chapter, we will start compactness. What you should keep in mind is the following. You should know the basic notions like isometry, extensions, the content of the theorems, when there is an extension, when there is unique extension, and so on. But don't memorize again proofs, okay? Uh, just try to understand them, but you should be able to follow the steps of the proof going back and forth. I don't mean that whenever you read it, you'll understand, you have to understand every step. Uh, what I expect from you is to, you will read each sentence, you will go back and read some definitions, some results, and so on, and then come back and you will understand that sentence, and it will go like this. So I expect you to understand the proof, okay, but not memorize. You don't have to like the proofs, okay. uh, Actually, I mean, if you understand something well enough, then you can just write down uh, your own proof, and you should try actually doing this. While you do this, you will realize how much you understand actually the material. Okay, it's a good uh, kind of uh, check whether you understand the material or not. You know, try to write down your own proof. Uh, we proved what? We showed that any metric space has a completion. Uh, just the analogy between rational numbers and real numbers. And we have seen that rational numbers is real numbers is unique in that sense. Real numbers with the absolute value metric is the unique extension of rational numbers with absolute value metric as a complete as a metric space. So it's the unique completion. That's why you haven't seen any other metric system or number system which contains rational numbers as a dense subset other than real numbers, because it doesn't exist. Okay, up to isomorphism there is only one such metric space. So in that sense, it's this stuff is very important. Okay, once you start with rational numbers and try to find a completion for that, you have to end up with real numbers. Okay, and I think it will be the end of today's lecture. So let me stop here.